let's firstly check the attendance. Hello, can you hear me?
Yes, 老师。
Okay.
Yes, 老师。
Raymond Kui, 20. Raymond Kui, 20. Raymond Kui, 20. Arding Ghana, 15. Arding Ghana, 15. Arding Ghana, 15. Noor Mohammed Biabidikov, 17. Noor Mohammed Biabidikov, 17. Noor Mohammed Biabidikov, 17.
I'm here.
Oh, okay. Biabidikov. Okay. Fine. Mohammed Syed-Dema, 34. Mohammed Syed-Dema, 34. Mohammed Syed-Dema, 34. Masudu Zaman, 5.
Yes, 老
Masud,
师。
okay. Ibrahim Rob Job, 29.
Yes, 老师 I'm here.
Okay. Mohammed Tamer Kia, 30.
没有老师。
Okay. Mikhail M. Safa, 5.
Yes, 老师 I'm here.
Okay. Solomon
Number
Hart,
6. Number 6.
yes. Temur Marik Daminov, 8.
I'm here.
Oh, sorry, and then you had 10. Sorry.
10.
Temur Marik Daminov, 10. Okay.
Okay.
Sador Dadajonov, 8.
Here, 老师。
Okay. Christ David
Yes,
Pierre.
老师。
Okay. Hasibu Rahman Noor, 14.
Yes, 老师 I'm here.
Let's see. Mihrab Hossein, 15. Mihrab Hossein, 15. Mihrab Hossein, 15. Mihrab Hossein, 15. Gentle Fetus, 21. Gentle Fetus, 21. Gentle Fetus, 21. Gentle Fetus, 21. Abraham K. Kromas, 22.
Yes, 老师 I'm here.
Okay. B. Sir Phillips G. Russell, 25. B. Sir Phillips G. Russell, 25. B. Sir Phillips G. Russell, 25. Solomon K. Sawyer,
Yes,
26.
老师 I'm here.
Okay. Bethlehem Telehuan Mamo,
Yes,
29.
Laoshi, I'm here.
Okay.
Yes, Laoshi, I'm here.
I see. I hear you. Next, Laikun Asifa, 30. Next, the equal alpha 30. Next, the equal alpha 30. Valery Butek 31. Valery Butek 31. Valery Butek 31. Valery Butek 31. Anna Akulova 32. Anna Akulova 32. Anna Akulova 32. The one Tobacco Gabriel 33.
Yes, Laoshi, I'm here.
Okay. Big Noir Ikram 34. Big Noir Ikram 34. Big Noir Ikram 34. Big Noir Ikram 34. Azamat Kalimulin 36. Azamat Kalimulin 36. Azamat Kalimulin 36. Okay. Let me share my screen. Can you see the slides? Hello? Can you see the
Yes,
slides?
Laoshi.
Okay.
Yeah.
Before we move on to today's new content, let's firstly have a brief review about our last lecture. Okay. So in last lecture, okay, we mainly discussed the ARM, Linux, GCC. This is a cross compilation tool. So what is a cross compilation? It is that we develop an application in a host machine that running a conventional system, while the developed application, although it can be compiled in our host machine, but it cannot run there. It can only run on the target machine, which is an embedded device running an embedded operating system. So within this toolkit, it also supplies several supported languages, including C, C++, and so on. So here, the toolkit supplies in the GNU GCC toolkit, including the CPP. Okay. So here it is PP refers to the preprocessor, while the G++, it is the C++ compiler. GCC, the C compiler. GCC bug, it is the shell script to create bug reports. While libgcc, this is the runtime memory in the GCC tool. While the lib std C++, by its name, we know that it is the standard C++ library. So it provides the most commonly used functions in the C++ language. So like the function, normal functions like the out, cin, and other standard C++ library functions come from here. The lib soup C++, this provide library functions supporting C++. Okay, so the main features of the so-called cross compilation environment Firstly, this environment is built on PC, okay, not an embedded machine. So it coexists with PC's compilation environment. So in general speaking, during the cross compilation, okay, we can still use the IDEs built upon the PC. But okay, the executable, okay, the second feature, the executable generated by the cross compilation can only run on the embedded device. Then remember this figure, okay? This figure demonstrates the cross compilation process using the ARM, Linux, GCC toolkits. So here, in this figure, it demonstrates the two possible compilation targets. So the first one is to generate the executable. The second one is to generate a library. So we see that the input to the compiler, ARM Linux GCC compiler, is the C source code and the head file. Okay, so after the compilation and the compiling process, okay, we know that the compilation, okay, consists of 4 phases, right? Okay, the first one is the pre-processing, the second one is the compiling, the third one, okay, is assembling, while the last one, is linking. So here, okay, the pre-processing and the compiling have already been done by the ARM Linux GCC's preprocessor and the compiler. Okay, then the next step is for the is generated assembly. The assembly will be fed into the assembler. Okay. So in the toolkits, it is the job of the ARM Linux AS. Here the AS refers to the assembler. So the AS takes the assembly code as the input and output the object file. Then from the object file, there is 2 paths. Okay, the first one comes to the library. The second one comes to the executable. So if we want to build a library from the object file, okay, then we're going to use the tool, okay, ARM Linux Air. Here, Air refers to term archive. So ARM Linux Air can create, modify, and remove the library. So essentially, okay, the so-called library, okay, is also combine several object files together, but it will list an index of the export function within the object file, okay, as the output of the library, which means that once an outside program that for instance reference this library, okay, like use the include something, okay, then it can use the exported function within the library to do more things. So the library itself, okay, although it also the bytecode, but it is not a completed program, which means that it cannot be run solely. It can be used by other programs, but it cannot directly run by itself, although it is also the bytecode. Okay. Okay, so we can see that finally it will have a symbol table. Okay. The symbol table is the refers to the global variables, okay, including the functions exported from the libraries. Also, sorry. Then, if you want to generate an executable, okay, then it's time to use the linker. The linker can link several object files and the related next. Okay, I see you. So next 30. So let me check. Next 30. Okay, I see you. Yeah, next time, please be on time. Next time, okay. Next. You are late for 15 minutes. Okay, so for linker, okay, it will do a linking, link the object files and the related libraries together. Okay. So it will adjust the code segment, data segment, and so on. And also the address, okay, especially the for the branch instructions, okay, also the variable reference, okay, like the pointers, all the addresses will be also adjusted. Okay. So this is the job of the ARM Linux LD. So this is the linker within the ARM Linux GCC toolkits. So it can generate an executable, or it can generate an reloc module. Okay. So this one is also this so-called module. Okay, reloc module. Is that the reloc stands for the relocation. So that's why we have two relocation. Okay, it's because that during we combine the object files and the libraries together, okay, the global variables, the address of the functions are also being adjusted. Obviously, the relocated. So that we have to generate this module. Okay, so this is how the ARM Linux GCC, okay, do the cross compilation. Okay, let's see today's new content. We continue to discuss different tools within the cross compilation. So we know that okay, the linking, okay, linking is a very important compilation phase during the entire compiling process. So how the linker, okay, can link multiple object and library files together. Okay. It actually follows a script which is called the linker script. If you want to say exactly what is the linker script, you can use such command to check it. Linux LD, okay, this is a linker command, okay, then minus verbose. So with this command executed, the linker script should be the default in kernel script, okay, because that if you can supply, okay, modified, okay, modified linker script by yourself, okay, but if you do not supply specialized linker script, okay, the linker will use some default script. Okay. Of course, if you are not very familiar with the compiler, okay, and the compilation process, it is better for you to use the default linker script. Okay? You don't have to try to create a linker script by yourself. Okay, unless you are really have confidence about yourself, and you are sure that you are really understand the entire compilation process, and you want to guide the linker by yourself. Okay? But anyway, so this is still possible, okay, to guide the linker, to let it to link the object files and the libraries together, following by your linker script. So let's say an example. So here, this one, okay, we use the VI. Okay, VI is a commonly used editor, command line editor under the Linux environment. Okay. So here we use VI to create a linker script called session LMDS. So this is the postfix of the linker script. So this is the content of the created linker script. Firstly, we determine, okay, the output architecture. Of course, okay, because after we use the ARM, okay, ARM Linux GCC to do the compilation. Then, of course, the outputted executables architecture should follow, okay, the ARM architecture. Okay. So this one is almost we cannot change this line. Okay. Then, okay, with by its name, okay, section. Okay. So here, within this link script, okay, we actually try to do something, okay, with the sections. Okay. So exactly what we do in this linker script. Okay. So we say that here the dot text, dot data, and dot BSS. Okay, remember what are them? Anybody can tell me what is the dot text, what is dot data, and what is dot BSS? Can anybody answer me? Let me pick up one. Okay, let's see. Okay, Sador, are you here? Number 8, Sador. Okay, then Christ, number 12, Christ. Number 12.
I'm here, Larshi,
Yeah.
but I have internet problem.
Okay,
Connection
Sador,
problem.
okay. Sador, please answer me. So what is the dot text section, and what is data section, and what is BSS section? Okay, maybe the things that okay. Hey, sorry. So remember, okay, when we discuss linking, okay, we say that there, okay, the linking, okay, for the input to the linker, okay, it is the object files and the libraries. So there are code, okay, obviously instructions. Also, okay, when we say the object file as yeah, despite of the instructions, there are also data. Okay. Here, data meaning refers to the global variables and the static variables. So here, the code section, okay, is actually the text section. Is here the dot text. So here actually, when you learn the operating system course, okay, actually dot text, dot data, and dot BSS, okay, they are the refers to the related segment within a process. Okay, I think you should have learned them. Okay, so actually they are also corresponding to the dot text and corresponding to the instructions. While dot data and dot BSS they contains global variables and the static variables. Okay? So remember that when we say the linking, okay, we actually combine the instructions within the multiple object files and the instructions from these several object files are combined together and being put as a new dot text section. While here dot data, okay, it stores the initialized global variable and static variables. While dot PSS, it stores the non-initialized global variable and the static variables. So okay, the corresponding variables within the object files are also grouped together and being put to a new dot data section and dot PSS section in the combined object file. Or we say the executable. Because after linking with the library, it actually can be executed. So essentially here, we see that this dot text, then here bracket, and within body it is a star left bracket dot text. Then similar here dot data dot PSS. So this means that still all the this is refers to the all the instructions from the input object file and the libraries are put here. Then here all the initialized global variable and static variables are put here, while the initialized non-initialized global variable and static variables are put here. Here, this dot text section in the newly generated executable should start from the address 1000000. While in the newly generated executable, the dot data section should start from 8000000. Actually, the effectiveness of this link script is to set the starting address of the dot text section and the dot data section for the newly generated executable. So here, dot BSS means that once the initialized global variable and the static variables are put here, and then immediately after them, the non-initialized global variable and static variables will be put following the data section. By default, the dot data will directly follow the dot text section. But after we use this link script to guide the compiler, obviously to guide the linker, to link the object file and the library together, then the dot text, this section may have some distance between the dot data section. So this is a simple example that we write a link script that just adjust the starting address of the different section within the executable. So what is the benefit? So we say that if we know the exact starting address of, for instance, of the dot data, dot data section, then we can directly infer the global variables address So it is better for us to do some debugging issue. Okay. So the command that to use the our self-written link script, the format is that ARM Linux LD -O ESP2. So this is the executable to be generated. Okay. Then hello.o main.o. Okay, these two objects is to the input object files to be linked. Then minus uppercase T. Okay, then section MDS. Okay, so this is script. Okay. Here the minus big map map.txt LC. Okay. So this means that after linking, okay, the section structure, okay, obviously section addresses, okay, of within the executable ESP2, okay, will be outputted to the map.txt. Okay, so we can check the related map information by using the minus map this option. Okay. And generally speaking, okay, this is just an example. Okay. In most of the time, we don't have to use this. You just know it, and that's okay. Then when you say the debugger, so we know that ARM Linux GCC, okay, it is although okay, it is a cross compilation toolkit, still okay, it is running on the Linux environment. So we know that okay, the GDB is a well-known okay debugger for the GNU okay compiler. So also it works for the ARM Linux GCC, okay, because ARM Linux GCC is also belongs to a GNU system. GDB okay itself is an interactive tool that works in command line mode. Any of you have has experience for using GDB? Anybody has used GDB before?
A built-in GDB maybe on a compiler on IDE, or just alone.
So if you have some experience that to directly use a command line to do some programming on the Linux, so you may have the experience for using the GDB. So have you learned Linux before?
A little bit, not much.
Not much.
You can use GCC, to compile.
Okay. Anyway, that doesn't matter. Okay. So GDB, GDB is generally widely used in the command line model. Okay. So not like the IDE. Okay. We know that IDE we have relatively more friendly, debugging methods. Okay. Sometimes, okay, because of some issue, we have to use this command line model debugger. Generally speaking, GDB has these functions for debugging: set breakpointers, single step execution, watch variables value, okay, modify variables value. Also, it has many other functions. Of course, okay. Set breakpointers. You know what is a breakpoint, right? Do you know what is a breakpoint?
Yeah, between codes.
So have you used any debug? Okay, for instance, you within an IDE like the Visual Studio. You know, okay. Masudu Danan, there. Can you tell me? Oh, there. Okay, Lavan. Say, Lavan, can you tell me how do you use the breakpointers?
You use the breakpointers to specify which part of the code you need to debug.
Yes, right. So in general speaking, okay, when we do the debug, right? Okay, of course, it goes after we write our code, okay, we test it and see something wrong, okay. Then we set a debug at a certain place of our piece of code, okay. Then we will say that, okay, if it will during running, okay, the system, okay, will stop. Okay, the program will stop at the set breakpoints, so that we can clarify that, okay, that which part of our code has something wrong. Okay, this is our very useful technique of mechanism for setting breakpoints. Okay. Also, the single step execution. Okay, so we execute the program instruction by instruction. Okay, also to say that which instruction, okay, has something wrong or not. Also the watch variables value. Okay, so usually, okay, it is used with the breakpoints. Okay, means that with the program case execution stop at certain instructions, then we will watch the current. There are some maybe we'll need to see the current key variables. Okay, also we can modify variables value, okay, to test our program. Okay, so this is some basic functions of the GDB debugger. By the way, okay, here GDB stands for the GNU debugger. Okay. So before using GDB, okay, we know that we need to provide some debugging information to the debugger. Otherwise, it cannot set breakpoints, or it cannot do the single execution and so on. So to do so, we need to compile the source code with some special option like the -G. So for instance, okay, if we use a makefile, okay, so the makefile is like the compiler compilation script in the Linux system. Okay, it directly guides the compiler, okay, to compile the entire project. Okay. So here, if we use the makefile, then we can define the C flags as the -G. Okay. Or we can directly use the GCC commands, okay, like that. Okay, GCC -G -O. Okay, hello.c. Then here the generate executable hello. Okay, will have the needed debugging information. Then for such executable that with the debugging information, then we can use GDB to debug it. We can use the GDB with the executable's name, okay, directly. Or we can firstly type in the GDB and with the character return and open the GDB console. Then we can use the file to this command and with the name, okay, to start debugging. So here, I say within the GDB console, okay, we can use different commands. So the break, and here in GDB that there are some commands that it also has some shorter version. For instance, the break, okay, break function means that it set a breakpoint at the function entry point. Okay. So for instance, if we have a function like the sum, okay, int sum, okay, parameter is the int a and int b, okay, and the return is return a plus b, okay. So this is a function sum. So if we set up use a command like the break sum, then once the sum function is invoked in your code, okay, the program will stop, okay, at the entry at the beginning of this code of the sum functions code. So here, the break can be short for just a single character B. So here you can just type in the B sum. Then we can also set a breakpoint using the line number. Okay, so you can just count the say which line of the piece of code you want to stop. You want to stop at there. Okay, then you can just type in the number and with the break command. Also, the break file command number. So this one is set a breakpoint at the certain line of a certain file. Then the break number if condition. So comparing with the single break number, okay, we can use some conditional breakpoint. So which means that if only when the condition is true, the breakpoint at the line number will take effect. So for instance here, suppose we use a command B5 if I equal to 10. So here is not use the double equal, just use a single equal. So this command means that we set a breakpoint at your program, line 5, the 5th line of code. But this breakpoint only takes effect when the variable i's value is 10. So only at this point, the program will stop at the line 5. Otherwise, it will ignore the breakpoint and simply continue to run. This is widely used to debug the program that using a using loop. But during the 10th loop, we want to stop at a certain point at a certain line. Of course, it can be used for the condition can be more complex. Depends on your program. Of course, if for your IDE debugger, you can also set the breakpoint to a certain line number, and also you can give the condition. It is similar, but here in GDE we just use the command line to do it. Then the clear, the clear is to delete the breakpoints set on a specific source file or line. So for instance, if we use a clear file name and the number, so which means that we will clear the breakpoint set at this file and the line number here. Now continue. This is to use the with the breakpoint. Because at the breakpoint, the execution is stopped. Then use the continue, or we say C. And then the program will continue to execute the program. Delete BP number. So because sometimes we use more than one breakpoint. Then the breakpoint will have its own number starts from 1 so that you can delete breakpoints use a clear with the file and number. Also you can just directly remove the breakpoints using its number. Then the command bt. This command is to display all call stack frames. So what is a call stack frames? We know that in most of cases, for relatively complex program, it's very common that we invoke a function A, and the function A invokes another function B, and the function B invokes function C. Then maybe at some place our program crashed or get something wrong, or may output some weird result, and so we want to do some debugging and want to know exactly how it comes out. And so for this case, we need to know the function call sequence. Okay, so how can we how or why we come to the problematic instruction, okay, or we come to the weird result, okay, or we come to the crash point. Okay. So that's we need to display the call stack frames. So this is a very important functionality for the debuggers. So let's see this figure. Okay. So this figure demonstrates a relatively simple call stack. So here you see that this piece of code, okay, in main, okay, int main, in its main function, okay, we have int x assigned with 2012, and int y, okay, I invoke a function f and fx, okay, it pass the variable, okay, x to the function f, and then in the main function it return 0. Well, in the function f, okay, it simply takes the parameter z and returns z multiple z. Okay. So simply, this is a very simple program. Okay. So we know that to start a program, okay, actually it is the operating system that to invoke the main function in your program. Okay, so the main function in most of time, okay, in most of time, it is the entry of your program. Okay. So we know that okay, the OS okay will create a process for your program, okay, and to execute the instructions from this main function's entry point. Okay. And let's say the call stack. Okay. We see that firstly, okay, the main function is being invoked by the OS. Then here the OS, okay, is also it also leaves a call frame, okay, in the call stack. So we see that, okay, this frame, okay, it is for the main, okay. Then in the main function, okay, it's called the function f, okay, it invokes function f. Then here, okay, we know that for each function, okay, once we invoke it, okay, it will push the return address, okay, and also the parameters, okay, to the call stack. So we see that here, return address, okay, and also its local variables. Now we can see this here for more clearly. Okay, so here this is a caller stack. Okay, it is a call list stack. So the caller, okay, is the one who invoke the function. Then in more details, okay, it is the callee. Okay, so the caller stack, okay, because of the caller, okay, for instance, like the main, okay, main, so corresponding to the function f, okay, then the main function, it is the caller, while the function f, it is the callee. Okay, so the function mains call frame is firstly pushed into the call stack. Then it is a call lead call frame to be pushed into the stack. So including its local variables, return address, okay, also the saved EBP, okay. So here the EBP is the base of the caller's stack, okay, the caller stack frame. Okay. Why we need so? Okay, it is because that, okay, once the callee, okay, the callee is done, okay, so its instructions are finished, okay, all have been executed. Then the return address, okay, sorry, this return value will be put back, okay, to the callers, so it may be received by the caller, okay. So it need to find where the stack frames of its caller. So it is use of the EBP, okay. So by the EBP, okay. So the callee, okay, because this callee, okay, if it invokes another function, then it will also be a caller. So essentially, with the EBP, okay, we can build a call chain. Okay. Obviously, that the callee can find its parent, obviously its caller, okay, during its call chain. Okay. Also, okay, follow this call chain, okay, we can know that exactly where the error happens. Okay. So this is the usage of the BT. Okay. It will demonstrate the call stacks with the related calls frame information. Okay. For each call frame, okay, it including the EBP, return address, and also the local variables. Okay. It should be noted that, okay, it is a stack. Okay. So at the high address, okay, then it is the first caller. Then following the second caller, the third caller, okay. The lowest one, okay, is usually the where the error happens, okay. The current running program, okay. Sorry, the current running functions instructions is in the is a call frame, okay, is in the lowest address in the call stack. Okay. Display exp okay, this is an expression, okay. So with this command, okay, we can display the value of an expression for each time the program stops. So why the program stops? Okay, because that we use breakpointers, right? Okay. So this is expression, okay, should consist of the program-defined variables. Okay, so you can only use the variables, okay, appears within the program. Then file, okay, this is to load the executable, okay, for debugging. Finish. This command is to run the current program until the current function returns. Well, help. This one is like the menu, like the man, MEN, okay, in the Linux, okay, to say the to say how the command, okay, to be used, how the usage of the usage method of the command. The info break, okay. So info break, this command can demonstrate the current set breakpoints, also including the number of times, okay, the breakpoint has been reached during the execution. So firstly, we can see the number of the breakpoints so that you can use, okay, the delete, okay, to remove the breakpoint by its number. Also, okay, we can see the number of times, okay, the breakpoint has been reached during the execution. Okay, so that it is also useful for debugging because sometimes, okay, we need to ensure that, okay, this certain instruction should be executed during an execution or not. Then the info files, okay, it will display the details of the debugged file. While info function, yeah, you display all function names. Info local, it display the local variables information, okay, in the current function. The info program display the execution status of the debugged program. Info var, okay, that displays all the global variable and the static variables names. Okay, so here these variables are the ones, okay, in the .data and the .bss segment. So all the global variables and the static variables. Kill, so terminate the current debugged program. List, show the source code snippet. Make, run the make tool without using GDB. So we know that make, okay, we will discuss it later. Okay, so this one make is to use the compilation script make file. Okay, make is also a compilation tools used by the GNU system that can compile the project, the C project, okay, using the make file script. Then the print, okay, so it print the value of the given variable. Next, it execute the line of source code without stepping into other function. Q, quit, exit from GDB. Run, execute the debug program. Step, so this execute a line of source code. Okay, if it encounters a program, step into the function. So combining with the next, okay, so be aware about that. Okay, so it means that if you use next, okay, if the next line of source code, okay, is a function invocation, okay, like the for instance, a assigned with fx, okay, then if you use next, okay, it will directly execute these instructions. Okay, then the execution within the function f will be automatically executed, and you don't enter the function f and simply move to the next line of source code of this function invocation. While if you use step, okay, then when you execute to the same line of code, okay, a assigned with the function f and x, okay, then you will go to the function f, and you will execute the instructions or source codes within the function f. Okay, so this is the step. I mean the step into. Okay, then watch. Okay, watch var. This one, okay, is to monitor the specific variable var. So let me say, okay, again, for next step, okay, so why we have need these two different, okay, one line, okay, execution commands, okay, it is because that, for instance, for a function, okay, especially, okay, it is some standard library function, okay, so we know that standard, because that the standard library function won't have any error. Okay, so but if you use the step, okay, then it will still come to the library's code and execute the instruction line by line. Then it will be time consuming and we cannot get much information from it. Okay, for this case, okay, we can simply use the next. Okay, to directly ignore the execution of the library functions, then we can come to the line of source code after the function invocation. Especially, okay, for some standard library function, it is very complex and contains many lines of source code. Okay, if you use steps, okay, you will for a more a possible problem is that that library functions are even call another function. That callee may call another again call another function. So you may get stuck in that function. So that for in this case we need to use next but not the step. But if we want to debug, especially you want to debug your self-written function, then you need to use the step to step into the function and check which lines of code has something wrong or not. So let's use a simple example, to show us how to use GDB. Let's say this piece of C code. So include the SDIO H. In the main function, we define a variable balance. 100 target is 1000 float. Rate is 0.1 and the year is 0. We say that then we use the do while do while loop. Then the interest. So you may notice that interest assigned with the balance multiple rate. So we know that it actually try to mimic you mimic some small bank, right? So the balance plus interest, right? For the other matter, you are too late. We have less than half an hour. Anyway, other matter, you are too late. Our course always starts at the 1:45. 1:45. So please be on time next time. Please other matter. So we say that then the year passed by 1. So we say that finally out of the loop, then we say that it will output the balance, number of years, the target balance. So how many years you need to reach your money grows from 100 to 1000 with a rate of 10%, right? But you may say that there are something wrong, right? Especially this line of code. It will try to say check in this loop condition. It will check that whether when the balance larger or equal to target, then the loop continues. But actually, this is a bug, right? It should be less than the target, so that we can know how many years are needed from the balance growing from the 100 to the 1000. For this piece of code, I think you can understand it, right? Anybody have any difficulty for reading this piece of code? Anybody have difficulty for reading this code? I think that since you have already learned the C++, so you should be able to know this piece of code. So firstly, to do debugging with GDB, then we need to use gzc -g. Then this one, we assume that we directly generate an IOUT. By the way, IOUT is the default name for the generated executable within the GNU GCC system. Okay, so it means that if you do not determine a name for your executable, then its default name is a.out. Okay. So here, then we use gdb a.out to start the program with gdb. Okay, let's set a breakpoint. Okay, so here b main. So the that we set a breakpoint at the entry of the main function. Then we run. Okay. Okay. It is stopped. Okay, at the first line of the main function. Okay. So the first line, okay, is here balance. It define a variable balance and assign 100 with it. And then we step. Okay, S is short for the step. Okay, so we continue to run the single line of the source code. Okay, the next line. Okay, it define the target. Okay, and define the rate and initialized it. Okay, also the year. Okay, then okay, we continue. Okay, it calculate. Okay, here. Okay, it enters the loop. Okay, the do while loop. But here the float interest assigned with the balance multiple rate. Okay, this is the first line of the code of the loop code. Okay, so here during execution, the bracket. Okay, and also some initializers like the do. Okay, while and also the comments are ignored by the GDB. They are not considered as a line of source code. Okay, so here for the do while loop. Okay, it directly come to the first line of code here. Also, okay, the next line of code. Okay, balance pass the interest and also the year passed by 1. Okay, so SSSS. Okay, we step. Okay, until we reach the line 13. So here, okay, want to say, okay, what is the current situation, okay, of the program? Okay, so we use the print. Okay, obviously use it shorter version p. Okay, to see the value of the different variables. Okay, so we say p balance. Then we know that because the balance, okay, plus with the interest, while the interest here, okay, is a balance plus rate. The rate is 0.1. Okay, we know the balance original value is 100. So here the interest is what? Is 10, right? Then balance plus the interest 10. Okay, then 100 plus 10, it is okay 110, right? And plus rate, okay, is here. Okay, then plus interest is here. Okay. Then we continue to step. Please be aware that the rate it is a float variable. Okay, so it has something after the many points. Okay, while the balance and the interest, they are integer. Then we run else. Okay, it will come to the while condition. So here, because it has a condition, you need to say whether the current value of balance larger or equal to target. So we know that currently, okay, the balance, okay, is 110, while target is 1000, right? So we know that the balance actually less than target. However, the do while, okay, the do while loop, we know that the do while loop continues when the condition is true. Okay. So of course, the condition here, is false. Then the loop, then here the loop ends. So we continue to run. Then it will come out of the loop and to run the printf this statement. So of course here because after the year, okay, the initial value of a year is 0, okay, while the loop just execute once, so we know that the year's value is 1, right? So here we set, okay, we want to say the problem, okay, say the P, okay, target is 1, the value is 1000, P year, okay, its value is 1, while balance its value is 110. Okay. So then we see the problem, okay. Why the loop, okay. So here actually the year, okay, the number of year, okay, is the number of the loop to be executed. So while the loop will simply execute once, okay, of course the problem comes out of the condition in a while. Okay. That's because that we want to know how many years are needed, okay, when the balance under the rate 10% can reach, okay, can reach to the target 1000. Okay. But here, because that we write a wrong condition while condition, so that the loop will break and run only once. So okay, after the debugging, so we know what is the problem, and we can modify the while condition, and then let the program run correctly. So this is a simple usage of the GDB. You can use GDB with more powerful functionalities. Okay, after we discussed the GDB, okay, for debugging, then we need to introduce the make. Okay. Why we need a make? Okay. Of course, we can use the GCC command to compile our source code. But for a large-scale project, there are usually hundreds or thousands of source codes. For so many source files, okay, if you manually type in GCC command to compile, okay, of course, it will be very, very inconvenient. Fortunately, okay, the GCC system, okay, GNU GCC system supplies us with the make tool to compile the project automatically. Also, okay, with the properly setting, okay, it can even achieve such functionalities. Okay. Once we have compiled the project, and after some time, okay, we may modify part, only a few, okay, let's say a few source files within the project. Okay. Then this time, we use make. We can simply compile these modified source files, and that's okay. Other source files that are not modified, the compiler will ignore it. Also, okay, if we modify a header file, okay, we know that the header file may be used by several or more, okay, source files. Okay. So in this case, when we use make, only the related source files, okay, will be recompiled. Okay. Other files will be ignored. So in this case, okay, in these two cases, we can save a lot of time. Okay. Because that to compile a large scale project, okay, it usually needs a really long time. For instance, if you compile a Linux kernel, usually you need more than 1 hour to compile the entire kernel. Okay, so, but next time, okay, maybe it did some version update. Okay, but actually this update may simply modify only 1 or 2 source files. Okay, so of course you don't want to compile the entire Linux kernel again, right? Okay, so you can just use make. Okay, to compile the modified file. Of course, it also works for other complex toolkits. So to use make tools, we need the make file to guide the compiler how to compile the source code. So with the make file, okay, we can use the make command to compile. Okay, this format like that. Make option, okay, macro define and target. So here the option indicates the makes behaviors. Okay, so we know that in the command line model, okay, we can supply the different the command with the different options to let the commands to do different things. Okay, then the macro define. Okay, and this is the value of the macro. Okay, this macro we will discuss later. It's like it's something the somehow okay like the macro okay we used in our C source code. The target okay then it means that it's one of the targets in the make file. So in GNU system okay so the make okay works with the steps as below. Firstly okay it read make file okay in the current obviously in the working directory. Then it read other make files in the include instructions. Then initialize the variables in make file. Deduce the obscure rules and analyze all rules. Create dependency chains for all target files. Depending on the dependencies, decided which targets to be generated. Finally, it will execute the build command. So in general speaking, okay, you will firstly read the make files in the project. So be aware about that. Okay, there might be just only one single make file. For some complex project, there can be make files within every subdirectory. Okay, so as to guide the compiler how to compile the files within a directory. Then, okay, it within the make file, okay, it also has some variables, okay, so corresponding to the different options and input file and output files, okay, so these variables. And also make file actually essentially it is define the compiler's rule, compilation rules. Okay, the dependency. Okay, we know that within among our source code. Okay, some files depend on other files, right? For instance, if you for instance if your one of the file okay include a header file okay then of course this file depends on that header file, right? Okay, then also okay maybe this file supplies some external function for another file, okay, then it also create another dependency. So the make will make clear about the dependency chain for all the target files. Then finally it will do the compilation. So this is a simple okay an example of the dependency. Okay. So for instance here the CPD okay this one includes two header files point and square. Okay, these are two header files. Also the pointers okay include the pointer.h while square okay include the square.h. So we see the dependency okay between the source code and between the CPD files and the header files. Then okay the object file generated from the CPD okay depends on this source file, okay, while the final executable okay are generated by linking this object file together. So the dependency between them here, so the entire dependency graph okay, we can create the entire dependency graph. This such dependency graph, okay, will be made clear by the make tool. Okay. It will firstly make clear about the dependency graph within the project. Okay. Of course, during the dependency graph creation, okay, they also need the help of the make filer. Make also has many more options. Okay, the mostly used, okay, are F, C, and D, I. Okay. F, okay, that means that use a certain file as a make file, while -C, okay, is specify a certain directory as a working directory. Okay. So because that when the make tool, okay, will firstly search for the make file from the working directory. Then -D, okay, you print the debugging information, while -I let the make tool to ignore the errors during the running process and do not terminate the make. Okay. For other options, okay, we can use the man, okay, this command in Linux, okay, to see other options for the make tool. Okay, so the make file rules, okay, as I just mentioned, the make file essentially are the rules to compile to guide the compiler. So we say that the rule is the basic unit of the make file. Okay. So each rule can describe a target file, okay, including the dependent files and the modules, and also the command, okay, to generate and update the target file. So the basic format of a make file rule is like that. Okay. Firstly, the target, then the optional, okay, the attributes, okay, then the rule OP, okay, here is how to do that, okay, and also the prerequisites. Then semicolon commands and the commands. Okay. So here the targets, okay, the target file list. The attributes are the targets attributes, but here is an optional. Okay, well rule OP. Okay, so here is the split target and the dependency files. And in most of cases, here this one, this so-called rule OP, is just the space. Okay, just one space. The command, okay, a command to generate the target file. So here, let's say a simple example. So this is a rule of within a make file. So what's that? Okay, we say that the target, okay, of this rule is to generate the task.o. Okay, so the task.o, yeah, this one, this object file, okay, is the target file to be generated. Then how to generate that? Okay, then it depends on, okay, the task.c space, okay, and test.h, okay, depends on this C file and this header file. Okay, so we know that we need to, it depends on these two files, but how to generate, okay, so which command is used to generate the test.o, okay, then we use gcc -c -g test.c to generate the test.o. So we say that, okay, we know that the -c, okay, is to generate the object file from the source code, while -g, okay, it means that, okay, this test.o, okay, includes the GDB, okay, the debugging information for GDB. Okay. So this is sample rules within the make file, including the targets, prerequisites, okay, and also the commands to generate the target file. So for the rules, Makefile, okay, it consists of two types. Okay, so firstly, the explicit rules. Okay. So within such rules, they clearly point out, okay, the target file to be generated, also the dependency files of the target files, and also the command to generate the targets. While the obscure rules, this rule, it makes it uses the make function, okay, it called the automatic derivation. So it means that okay, we provide partial information, then the make, okay, will can guess, okay, what we want to generate and provide the needed commands. While the variable definition, okay, so in Makefile, okay, we also need to define a series of variables. Okay, actually they are generally strings. So when Makefile is executed, okay, the variables in it will be extended to the corresponding reference position. So here, let's see more clear about it. Then the file instruction, okay. So firstly, the reference are another Makefile in one Makefile. Okay. Then it can specify the valid part in a Makefile depending on some condition. Also, okay, it can define a multi-line command. Okay, then we can also have comments. Okay, so the comment line starts with the pound sign. So the variables in Makefile, okay, like the macro, okay, in C or C++, okay, so represent the text string. Okay. So when a Makefile is executed, okay, they will be automatically expanded in the place where they are used. So like the in the pre-processing process, okay, in the compilation. Okay. But unlike the C or C++, the variables in Makefile can be changed can be changed. Okay. So the variables can be used in target, dependent target, command, and other parts of the Makefile. Okay. So remember, okay, we just discussed the target, dependent target, command, okay, and the command to generate the target from the dependent target. So the definition format of the variables, okay, so like is also like that, okay. Name assigned value, okay, it contains characters, numbers, underscores, and so on. Remember, it is case sensitive. So there are three assigned symbols, okay. But here you just know it, then that's okay. Like the string operation in the C++. Also, okay, the Makefile variables, okay, if you want to reference it, okay, you can use a single dollar. Okay. So when processing the variables, okay, so make will scan the entire Makefile to determine the value of all variables. Okay. So the variables can be used after the definition, and the values given last time are used. So like that. Okay, so this is a usage of the variables. So essentially, okay, it is the program.o, full.o, and utils.o here. Here. The definition of a variable can appear in the three places: Makefile, make a command line, and shell environment. But the priority between them, okay, the make command line and Makefile and shell environment. So for instance, okay, so this is the Makefile example for such a small project. Okay, we said to generate a main, okay, we need the main.o, point.o, square.o. Okay, then how to generate a main.o? Okay, we need from the main.cpp point.h, square.h. While for point.o, okay, we need point.h. While the square.o, okay, square.h, square.h. So this is the dependency and how to generate how the makefile are used for the small project. Okay, time is up. We stop here today. See you next time. Bye bye.
麦老师。